All right, let's look at this problem called binary preorder traversal. So the preorder traversal for binary tree, we have to print, and we also say the follow-up that hey, the recursive solution is trivial, but you do it iteratively. So we'll discuss that as well. So let's first quickly talk about how preorder traversal is done. So let's take out some random tree, let's say 1, 2, 3, 4, 5, like that, and maybe some 6, 7, 8, 9, and 10. Let's say this is your a tree. Now, when we say pre-order, essentially what it means is that you first print the root values, and once you print the root, then you do the same thing recursively on the left subtree, and then you do the same thing recursively on the right subtree. So what that means is for this tree, you start with the root, which is 1. Then you go to its left subtree. So first you will handle all of that, and only then you will handle all of this. So first handle the left subtree. Again, in the left subtree, you do the same thing recursively. So now first you print the root, which is 2. Then you handle the left subtree of this guy, which is just this, and then you handle the right subtree. So when you go to left subtree, it is 3, and you do the recursively for itself. Then you go to 5, then you go to 4. Now the left subtree is done. Now you go to the right subtree of 1. So you start with 6, go to its left subtree and go to the next right subtree. So 7, 8. 8 does not have any left child, go to its right child, 9, 10, right? That's how the Preorder traversal is built. So this condition, if you write it recursively, it's quite basic. Obviously, there will be a base condition where root is null, which is what you will use to terminate. Let's quickly write the recursive approach first. So essentially, we have to return a list of integer. That's what we have to print. So let's define that. So list of integer result equals to new array list, and this is what we will return. And in between, we'll call a preorder function where we will pass the root node and the result. And let's implement this function. So you do void preorder. You take in a tree node root, and you take in a list of integer called result. Now, base condition is if root is null, well then you return. Otherwise, in the result, you will add root's value. And now you'll handle the left subtree and right subtree recursively. So your root dot left result and preorder root dot right result. That's it, right? Let's run the code. Okay, get some errors, try and fix them. Incompatible type cannot convert into list. It was not a list of lists, it was just a list. All right, run again. And submit. And it works. Now let's try and talk about the uh, solution or the approach where you can do iterative. So now we want to talk about the iterative approach. Essentially, when you're doing recursion, there is some sort of stack involved. And now, how can I do it recursively? Well, if you really look about it, what it's happening is pre-order is sort of similar to DFS, right? Where you're going to through one of the child till it's complete and all, and then it's right child, right? And if you know how to do DFS iterative, then you can easily do the iterative way of pre-order. If you don't know, we'll talk about it. So the way to do that is, so this was your tree. What you use is you use a stack, and in this stack you initially push the root, right? And after that, what you do in this stack is you pop the element, and then whatever element is popped, then you push, first you push the right child, and then you push the left child, so that on the top you'll have left child, which is what you want to process first, right? And just keep doing this recursively till your stack is done. To make it clear, let's go here. This was the array. This is our stack, right? So first we add one root into the stack, and that's it. Now we look at the stack. Is the stack empty? No. Then remove the element from the stack, add it to our result list. And next is you push its right child, which is 6, and then you push its left child, which is 2. And now, again, is the stack empty? No. Then you pop the top element, print it. Whatever the element you popped out, first push its right child, then its left child. So push its right child, which is 4, then push its left child, which is 3. And now we get 3, push its right child and left child. It does not have a right child, so only push its left child. And you print pop 5, right? Now what's next element at this stack? 4. So pop it out, print it, push its children. It does not have any children. All right. What's the next guy? Well, the next guy is 6. So print 6, push its right child and left child. Right child is 8, left child is 7. At this point, who is top of the stack? 7. Print it, push its right child and left child. Doesn't have any. All right. Then you come to 8. Push its right child first, which is 9. No left child. All right. Element popped. 9. Push its right child and left child. No right child, only left child. 10. Pop 10, print it, no children, and we get the answer, right? So that is how we can do it iteratively, essentially using this approach. So let's build the algorithm for iterative traversal as well. So we close this, we reset the code. So here we do is we want to save the result in this list. So let's build that. And we are also going to use now a stack of tree node. We'll call it stack equals to new stack tree node. Can root be null? That's our question. So let's see, is something like that mentioned? Number of nodes can be 0. So if root is null, well, I'll just return result right away. Else I'll do stack dot push root. And now while my stack is not empty, what am I gonna do? I'll go pop the element out of the stack, add it to the result list. So and now push the right element first. So if node dot right is not equals to null, I'm gonna push it. So and then I do the same for the left element. And at the end, I'm gonna return the result. So that's the iterative way of doing it. Let's run. Let's accept it. Let's submit. And it works out. All right.